We were introduced to collections in the previous video, where we learned about the ordered collections like vector, vector DQ, and linked list. Now we'll continue with the next type of collection, maps or key value stores. Think of it as a lookup for values against unique keys, like a phone book. You look for a name in it. Once you find the name, the phone number will be the value attached to it. Rust has two types of maps, HashMap and BTreeMap. HashMaps are the most commonly used maps in Rust. It takes a key and stores a corresponding value to it. All the keys should be of same data type. Similarly, all the values should be of another data type. It doesn't matter if both keys and values are of same data type, but you can't change it later once you start using it. Needless to say, since we are storing values against certain specific keys, all the keys must be unique, so that Rust compiler can identify them. Hash maps are actually implemented in Rust based on hash tables following the Swiss table architecture. That's a whole different topic in itself, so I'm not going to explain it here. Let's see a simple program to show how hash maps are used. First things first, to use HashMap, we need to import the module. Now we'll create a contacts hash map. Here, the name of the contact person is the key and the contact number is the value. This syntax means &str is the data type for all the keys to denote the contact names as string literal, and I32 as the data type for values since we would only have numeric inputs here. To add values against keys in the hash map, we can use the insert method and pass the key as the first parameter and then the value as the second parameter. Just imagine that this 100 to be the phone number. We'll insert another entry for Bob. We can now print this hash map to see the contents. After running, you can see how the keys and values are stored. Now to retrieve a value from the hash map, we can use the get method and pass the key. This will get the value for Alice. The get method in Rust almost everywhere returns an option enum, so we can use the match to handle the value retrieval process. If we run the program now, we get the value 100 which was stored for Alice. Now if we use a key which is not present in the hash map, say John, this will not return any value, so we are getting not found for the second case. For these contacts, you can see there are so many methods available to manage the data in the hash map. Let's see a few useful ones. To check if a particular key is available or not, we can use the contains key method. This will return a boolean to denote whether the hash map contains that key or not. Here we had Alice present, so we get true, but since John was not present, we are getting false. There can be situation when we just want to get all the keys from the hash map. In such a case, we can use the keys method. Now if we run the program, we get all the keys from the hash map. Similarly, we can get all the values as well. You can see now all the values are printed. I should mention one thing here, that these keys and values methods return the reference of the keys and values. This would be evident if we write for key in contacts.keys. You can see here this key variable for the iteration is the reference of the string slice. That's why the double ampersand symbol. So after running this keys method, we can still use the contacts hash map to get the values, since it still has the ownership. But there is another set of methods, into keys and into values, which consumes the hash map and returns an owned iterator. That means we can't use the contacts hash map anymore after using the into keys method. If we run it, we will get an error. To get key and value, we can use the getKeyValue method. This again returns the option enum. So for Alice, we get both key and value, but for John, we get none. The entry method returns the entry for the key. If we print this by running, we can see both the key and value. Then how is it different from getKeyValue method? The getKeyValue method returns the data as an option enum, but the entry method returns the entry enum. This will help us modify the value of the key in place by using the method chaining. For example, if we want to modify the value of Alice, we can do it like this. This is called a closure. It is similar to what we call the lambda function or anonymous function in other programming languages. We will learn closures in detail later in this series. Here, it is just incrementing the existing value by 1. So if we run it, we get 101 for Alice. Let's do the same thing for John. We don't have John added in the HashMap as key, so let's see the behavior. For Alice, we got an occupied entry, but for John, we got a vacant entry, since John is not existing in the contacts. There is another method called OR_insert, which we can use here. It will add a value against a vacant entry. Now you can see 5 against John. If we add this OR_insert for Alice, it won't have any impact, since Alice was already existing in the HashMap. There are a lot of methods available for HashMap. I would recommend you to try them out. Even if I explain every method in detail, you won't get it until you practice it by yourself. So try them out and get used with these methods. You can also share your findings in the comments as well. That will help everyone. Moving on to the next type, we have the BTreeMap. Here everything is same as HashMap with one difference. The data stored in BTreeMap is always sorted. By sorted, I mean that the keys are always in sorted order, no matter in whatever order you insert them. If the keys are strings or characters, it will be in alphabetical order. And if we have numerical keys, then those will be in ascending order. We'll try to understand with an example. This is the same code that we have seen before, but instead of HashMap, we are using the BTreeMap. It will also get printed the same way. Now, here Alice is appearing before Bob alphabetically. But you can say that we have inserted Alice before Bob, that's why we are getting in alphabetical order. That's not the case. We can find that out by inserting few more entries. At first, we'll add Tim. Before Bob, we can add John. And after John, let's add Alex. Before we run the program, let's figure out in which order they should appear. First should be A, but with A we have two names, Alice and Alex. First two characters are same, so the third character E in Alex is before I in Alice. So first Alex, then Alice, next we should have Bob, then John, and finally Tim. Let's see if that's the order we get after running. We get Alex, Alice, Bob, John, and Tim. That's exactly matches the alphabetical order. For numerical keys, it will be in ascending order. I don't think I need to show you an example for that. What I need to show you is that if we get more complex type of keys. For example, if we have tuple as keys. Here we added 3 entries in the BTreeMap, where the keys are tuples. The tuples contain the date as 3 values, first the year, then the month, and day at last. In this case, it will consider the lexicographical order. Basically, this means that the ordering happens based on the underlying elements. So the first value should be 2025. Next 2 years are same, so it will check the next element, which is the month. They are also same, so it will check for the day. Here 1st Jan should appear before 2nd Jan. We can verify that by running. We get the values printed exactly in that order. First 2025, then we have 1st Jan for 2026, and last we have the 2nd Jan. By the way, this is a way to iterate over the values in maps. I said maps intentionally because this applies for both HashMaps and BTreeMaps. Here we are taking the reference of the map and the values are unpacked using tuple unpacking. These values are also references, not owned. The keys can be even more complex or custom types, something like a struct. In that case, the struct has to implement the ORD trait for ordering. Here is an example. First, we created a custom type called person. This derive syntax is a macro that automatically writes code for us. Debug allows us to print the struct. EQ and partial EQ allows us to compare if two persons are exactly same or not. Then we implemented the ORD trait. This is the compare method where it compares self with another person struct. First, using this same method, it compares the age and try to match with two possibilities. First, if the age for both the persons are same, then it will compare the name alphabetically and return the value. If the age is different, then it just returns the result, which is the order denoted by this ordering enum. ORD trait is for types that always have a total order, like integers. On the other hand, partial ORD is for types that might not be comparable. For example, floating point numbers, where not a number exists. Since our person struct always has a clear order, we just tell partial ORD to use the logic we already wrote in ORD by using this line as the option of ordering enum. Now we are inserting few entries using the person structs as keys and role as the value and printing them one by one here. We order by age, so youngest Alice should appear first. Bob and Charlie both are of age 30. As per our logic, if ages are same, then it will compare the names. So Bob will appear before Charlie. Now let's run to verify. We get Alice first, then Bob, and Charlie at last. Since both the maps are same except the sorting factor, most of the methods in HashMap are also present in BTreeMap as well. Two such methods that I didn't cover in HashMap but are also present in both HashMap and BTreeMap are remove and remove entry methods. Coming back to our previous example, here if we want to remove a particular entry, we can use the remove method by passing the key, and that entry will be removed from the map and it will return the option enum with the value if the key was existing. I am removing the entry for Alice and Jim. After running, we can see sum of 100 for Alice and none for Jim, because Jim was not a key existed in map, and in the printed map after removing, we don't see Alice anymore. Remove entry method is the same thing except it would return both the key and the value as the entry instead of just the value. Let's try that as well. We get both key and value for Alice and none for Jim, and also the entry for Alice is removed from the map. Because of the sorting feature of BTreeMap, we can now definitely determine the first and last entry in the map, which we couldn't do in HashMap. That's why there are a few specific methods available in BTreeMap. We'll run it and explain. We have the first key value and last key value to get the first and the last entry in the sorted map as references. Pop first and pop last removes the first and the last entries and also returns them. First entry and last entry methods are also return the same thing but for in-place operations, like we have seen during HashMap. After popping first and last entries, next entries became the first and last here. There are two useful methods in BTreeMap that help manipulate multiple BTreeMaps. One is append and the other is split off. It will be easy to understand with an example. Let's run it first and then we'll explain what happened. Here we have two BTreeMaps. The first map has the key 1, 2 and 3 and the second map has keys 3 and 4. So you can see 3 is a common key for both the maps, but the values are different. In map 1 we have lowercase c and in map 2 we have uppercase C. Now what append does is that it merges two maps. Basically it moves all entries from the second map to the first map, and in that process if it gets a duplicate key then it will overwrite the value. So when this line is executed, all the entries in map 2 will move to map 1, leaving map 2 empty, and the key 3 is duplicate in both. So the value of map 2 overwrites the first. You can verify that in the console. Split off splits the map at the key that is passed. Here it is 3. So map 1 will be left with keys 1 and 2. Map 3 will be having 3 and 4. Same is printed in the console. One last method I will show you here, that is the range. Here we can iterate through entries of the map by giving a range. This is possible only because the map is sorted, so the result becomes predictable. In this example, we are printing only the fruits whose name starts with A to C. If we run the program, we can see date is not printed since range did not cover the D. This range method returns the reference for the entries for viewing. However, if you have a requirement to edit them, you can get the mutable reference by using the range mute method. Now we can change the count by dereferencing it and assigning a new value. Now if I run, all the fruits are of 15 kgs. That's all about maps in Rust. Maps are very useful while implementing many algorithms. The more we practice it, the better we can use it. So that's all for now in this video. Share your feedback in the comments and don't forget to like this video and subscribe to the channel. We'll see you in the next one.